Welcome to The Explainer. I am so incredibly thrilled you're here today because we're about to completely shatter everything you thought you knew about the fiery mountains we call volcanoes. We're going to deconstruct the mechanics, the history, and the literally cosmic scale of these geological giants. We're going to look at exactly what drives them, how they actually build our world, and, how they occasionally threaten to tear it all apart.
So, let me ask you right off the bat, what comes to mind when you hear the word volcano? If you're like most people, you're probably picturing that classic Hollywood stereotype. You know the one, right? A steep, towering mountain that violently blows its top, sending these rivers of glowing red lava down its sides. And sure, while that absolutely does happen, the real story of volcanic activity on our planet is far more diverse, way stranger, and honestly, a lot more fascinating than the movies ever show us.
Well, time for a little reality check. The vast majority of Earth's volcanoes, they aren't mountains on land at all. They're actually hidden deep underwater, right along the ocean floor. In fact, back in 2018, scientists detected these mysterious humming sounds echoing across the entire globe. Turns out, it was a massive submarine volcano forming off the coast of Mayotte. And it gets even weirder. Not all volcanoes erupt molten rock. As we'll see a bit later, some erupt massive slurries of mud, and others, way out in the deep solar system, literally erupt ice.
Section 1. The Plate Tectonic Engine, driving the chaos.
To really understand these phenomena, we have to look way beneath the surface. Earth's rigid outer shell isn't just one solid piece. It's more like a constantly shifting puzzle of tectonic plates sliding over a really ductile mantle. Now, most volcanic activity happens right where these massive puzzle pieces meet, but they act very differently depending on how they interact. At divergent boundaries, like the Mid-Atlantic Ridge, plates are pulling apart. Hot mantle rock just creeps up, creating new oceanic crust in relatively gentle, mostly underwater eruptions. But at convergent boundaries, it's a totally different story. Here, plates collide, and one dives right beneath the other. This destroys the crust, melts it down, and creates this thick, sticky magma that results in the incredibly violent, explosive volcanoes we see in places like the Pacific Ring of Fire.
But what about the rule breakers, the volcanoes that pop up right in the middle of a plate, nowhere near a boundary? Well, that brings us to hotspots. These are formed by massive plumes of hot material rising all the way from the core mantle boundary. We're talking 3,000 kilometers deep. As a tectonic plate slowly drifts over this stationary blowtorch, the plume just burns right through it, creating a chain of volcanoes. This is exactly how the Hawaiian Islands were formed, and it's actually what's currently powering the massive Yellowstone caldera in North America.
Section 2. Shapes, Sizes, and Eruptions. Volcanic Anatomy. Now that we know where magma comes from, let's look at why some volcanoes just ooze, while others completely explode. It all comes down to chemistry, specifically the silica content. Take felsic magma, for example. Magma with high silica is thick. It's highly viscous. And because it's so thick, it traps expanding volcanic gases until the pressure just becomes too great, and boom, you get deadly, catastrophic explosions. On the exact opposite end, mafic magma is super low in silica. It's fluid, it's runny, which allows the gases to just easily bubble out and escape, and that creates those gentle, fast-moving lava flows that we associate with Hawaiian Shield volcanoes.
When a volcano does finally erupt, it unleashes a truly terrifying arsenal. First up, you have volcanic gases like carbon dioxide and sulfur dioxide. These invisible, toxic emissions can silently alter our global climate. Then, of course, you have the lava flows. And finally, tephra. This is basically everything blown into the air, from massive car-sized boulders, literally called volcanic bombs, all the way down to fine, choking volcanic ash that can collapse roofs and bring down airplanes. And here's the crazy part. It's often those invisible gases and the choking ash that cause far more devastation than the slow-moving lava itself.
But what happens when rising magma meets water? Well, you get a phreomagmatic eruption. It goes like this. Step 1. Magma rises through the crust. Step 2. Instead of reaching the surface normally, it collides with a pocket of subterranean groundwater. Step 3. That water is instantly superheated, flashing right into steam and causing this rapid, immense pressure buildup. And Step 4. A cataclysmic steam explosion that just blasts the surrounding rock to pieces. It is quite literally a geological pressure cooker blowing its lid.
Section 3. Rating volcanic activity. Measuring the power. So how do scientists actually measure and classify the sheer, terrifying power of these earth-shattering events? They use something called the Volcanic Explosivity Index, or VEI. It's a scale from 0 to 8 that categorizes all this chaos. It starts at the very bottom with Hawaiian eruptions, which are those gentle, effusive lava flows. As we move up the scale, the magma gets thicker, way more gas-rich. We pass Strombolian and Vulcanian eruptions, all the way up to Plinian eruptions. Those are named after Pliny the Younger, who actually witnessed the destruction of Pompeii by Mount Vesuvius. Plinian eruptions blast these catastrophic columns of ash tens of kilometers into the stratosphere, literally blocking out the sun.
And at the very top of that scale, VEI 8, we hit the supervolcanoes, 1,000. That is a staggering number to wrap your head around. To even be classified as a supervolcano, a single eruptive event must eject at least 1,000 cubic kilometers of material. That's enough to alter the entire planet. These eruptions are so incredibly massive that they completely empty out the underlying magma chambers, which causes the ground above to just collapse into these giant craters called calderas. Think Lake Taupo in New Zealand, or of course, Yellowstone.
Section 4. The Human Connection, Hazards and Benefits.
Let's shift gears and talk about the profound, and honestly sometimes contradictory, impact volcanic activity has on human civilization, our survival, and our global climate. Throughout history, volcanoes have literally shaped human destiny. Around 70,000 years ago, the Toba supereruption in Indonesia is thought to have caused a volcanic winter so severe it actually created a genetic bottleneck in early humans. Fast forward to 1601, and sulfur dioxide from the Huayna Putina eruption in Peru caused a devastating famine all the way over in Russia. In 1815, Mount Tambora gave us the global year without a summer. But look at 1991, modern science finally steps in. High-tech monitoring of Mount Pinatubo allowed for a massive evacuation that successfully saved 20,000 lives. We are finally learning how to survive them.
But look, living near a volcano is the ultimate double-edged sword. Yes, the hazards are catastrophic. You've got pyroclastic flows that incinerate absolutely everything in their path at 850 degrees Celsius, devastating acid rain, global aviation disruption. But the benefits are surprisingly vital. Volcanic ash breaks down into some of the most incredibly fertile soil on the entire planet. The heat can be tapped for clean, renewable geothermal power. And for millennia, humans have used a soft volcanic ash rock called tuff for construction. The Romans used it to build their empire, and the Rapa Nui used it to carve the famous Moai statues on Easter Island.
Because of these incredible benefits, millions of people live right in the shadow of active vents today. This creates a really complex risk landscape, and it's exactly why scientists closely monitor the Decade Volcanoes watch list. This is a specific list of 16 volcanoes singled out because of their history of destructive eruptions and their dangerous proximity to huge populations. We're talking about mountains like Rainier in the US, with its immense risk of massive mudflows called lahars, or Vesuvius in Italy, sitting right over the city of Naples. These specific giants require constant high-tech gas and seismic monitoring to ensure we get that vital early warning before they finally wake up.
Section 5. Volcanoes in Deep Space. Cosmic Scale.
To truly deconstruct volcanoes, we have to expand our perspective outward. We need to move beyond Earth's atmosphere and explore the mind-bending cosmic scale of volcanoism in our solar system. Consider our planetary neighbor Venus. A staggering 90% of its entire surface is composed of basalt rock. So what does that actually mean? It means that massive, ancient lava flows have completely resurfaced and dominated the planet. From what scientists can tell, Venus may have experienced a major global resurfacing event about 500 million years ago, driven entirely by monumental volcanic activity.
And then there's Mars. Mars is home to Olympus Mons, an extinct shield volcano of truly incomprehensible size. It is the tallest known mountain in the entire solar system. It completely dwarfs Mount Everest and literally anything else found on Earth. It's a great reminder that while Earth's tectonic plates keep our volcanoes relatively contained by moving them away from their magma sources, on planets without moving plates, a single volcano can just sit right over a hotspot and grow for millions of years to truly colossal proportions.
But honestly, perhaps the most mind-blowing concept of all is cryovolcanism. Sure, Jupiter's moon Io might have lavas that exceed 1,500 degrees Celsius, but out in the deep, frigid reaches of the outer gas giants, things get bizarre. On moons like Europa and Saturn's Enceladus, we don't see molten rock. Instead, we see volcanic activity where liquid water, nitrogen, or ammonia erupts violently into space and instantly freezes into ice. They are, quite literally, ice volcanoes.
Which leaves us with this final, thrilling thought to ponder. We know that here on Earth, volcanoes brought essential gases to the surface, shaped our atmosphere, and provided the thermal heat and chemical nutrients that very well may have kickstarted early biology. So, if volcanoes act as these vital, life-giving engines of planetary evolution here, what unseen forces, what potential for life might those alien ice volcanoes be brewing in the dark, frozen corners of our solar system? Thank you so much for joining me on this explainer. Keep asking questions and never, ever stop exploring.